Yeah, okay. So I'm gonna get started, and we can kind of dig through the session. So my name is Jacob Tomlinson. I'm an open source software engineer. I work on Dask and Rapids and a few other things within NVIDIA. Now we've got like a 2-hour session now, so these are like reasonably long workshops. I'm gonna like break it up, and there'll be breaks and all that kind of stuff. Feel free to kind of move around as sessions come and go. But to give you like a little bit of background about me, I'm based in the UK, as you can tell by my accent. I am like physically here at the moment. I wasn't able to travel for this event, but I'm based down in Exeter. I used to work in weather and climate sciences in the kind of HPC side of things. So I have a lot of experience with HPC, cloud, Kubernetes, Docker. I come from like a sysadmin background. I've turned software engineer over maybe the last 5 years or so. So that's kind of my expertise. As I said, I work for NVIDIA. Now, I like the main project that I'm attached to in NVIDIA is a project called RAPIDS, which is like a set of open source Python tools that are designed to accelerate data scientist workflows. But this talk isn't like really about any of that. This talk is mainly focusing on Dask. If folks have questions about like GPUs and data science and all that kind of thing, I'm more than happy to like talk about it and answer questions, but that's like not the core like intent of this. So within Rapids, there is a project called Dask, which is like another kind of separate open source Python project that allows you to scale out your Python workload. That's what we're going to be talking about today. I'm like a core maintainer of that project and have been for since kind of 2017-ish. So to give you like a bit of an outline of this session and a rough idea of where I'm going with it, I'm going to start with like a bit of more of like a talk, I guess, about how Dask is integrating with Kubeflow. We've been doing a whole load of work on Dask over the last 6 months or so, built on top of kind of existing Kubernetes support in Dask, to get to a point where we now have really nice support for Kubeflow and like a much deeper integration there. So I'm going to talk a little bit about that, and then we'll take a bit of a break. That'd be maybe like 25 minutes, take a bit of a break. And then I'm going to kind of dive deep, and we're going to dive deep into Dask itself. So I can start off with Kubeflow and ML workflows and stuff, but then we're going to dive right down to how do I take Python code and accelerate it, distribute it, scale it, all that kind of stuff. So we'll talk about data frames. So if you've used Pandas before, this will feel familiar. We're going to talk about arrays. So if you've used Numpy before, it'll be familiar. We're going to do some machine learning, kind of a la SciKit-Learn, and then talk about some of Dask's internals, like the dashboard and bags and futures and how we deploy Dask and how it distributes calculations. So that's going to be like a 90 minutes broken up with some breaks in the middle. And all of that like chunk of the workshop, I'm going to do as like an interactive thing on Binder. So if you've not used Binder before, it's like an excellent hosted platform where you can work through notebooks. I've got it open here just to make sure it actually loads. It seems to be queued at the moment, but I'm waiting to get into that. So we'll kind of come around to that later, but you should all be able to get into like an environment, like a Jupyter-like environment where you can run some Dask code along with what I'm doing in the examples here, kind of experiment and have a look yourself. So hopefully that'll be useful. I decided to do it in Binder because it's much easier than trying to figure out how to get you all like the Kubeflow setups that I'm going to talk about at the beginning. So I'm going to dig in now to the talk stuff about Kubeflow. So Dask on Kubeflow. Before we can talk about Dask on Kubeflow, yes, let me just jump later in the presentation. So there's a question in the chat about the link to the binder. So there is a slide here. I'll leave it on the screen for a few seconds. If you head to this GitHub repo, there is like a little launch binder link. You can click that, it'll launch the binder. It's probably good for folks to like maybe start getting that loaded up, given that I seem to be in some kind of queue for myself, so that when we get around to that point of the session, we can kind of get started straight away. So I'll leave that there for, awesome. It's in the chat. That's even better. Perfect. Thank you very much. Right. So let's jump back here. So before we talk about Dask on Kubeflow, I'm going to talk a lot about like what is Dask. So it may be familiar to some of you, but I'm going to kind of start from the beginning and tell the full story. So as I said before, my background is kind of weather and climate sciences. I spend a lot of time working with scientists who are trying to do their work, right? Taking in data, transforming it, working with it doing statistics on it, whatever their thing, whatever it is that they're doing. And a lot of folks in that area are moving over to Python. And some of the biggest challenges that they were kind of running into was like memory issues. So like weather models are huge, data coming out of weather models is huge. And so like one of the early things that we needed was, how can I work with a 2 terabyte data set? I can't load it into memory on my machine. I'm going to have to like step through it in chunks. And rather than doing that kind of manually by like, having a bash script that loops over my code, running it many times, we looked to projects like Dask. And so I kind of got involved that way and started contributing to it, building it into tools that we were using then. So Dask, the idea of Dask is that it will take Python code that traditionally doesn't scale very well, doesn't utilize all of the cores in your machine, and it kind of breaks up all of your calculations so that it can leverage that. And you can leverage multiple cores in a machine, or you can leverage multiple machines in a cluster. So it's very flexible and very good for beginners, because the Dask workflow is exactly the same whether you're running it on a laptop or whether you're running it on a large supercomputer or cloud platform or wherever. Things feel kind of consistent. And Dask also tries to match existing APIs of Python libraries within the PyData ecosystem. So if you know Numpy, if you know Pandas, if you know SciKit-Learn, Dask will be super familiar because it just literally implements all the same APIs. Sometimes you can even just like switch the imports out, and that's enough for you to get going. So the way that this works under the hood is that Dask kind of chunks everything. It breaks everything down into pieces. It constructs all of those pieces into graphs, and then it has a scheduler that can execute through those graphs. So if we talk about arrays for a minute, if you have NumPy arrays that are too large to fit into memory, you can instead create like a large Dask array that represents all of that data, but that is still made up of small individual NumPy arrays that it swaps in and out of memory and does its calculations. You can see a small code example here showing how to create an array. Then moving from arrays to something like a data frame, we do exactly the same kind of thing, right? So if you're used to using a Pandas data frame, we just chunk those up. So when we're talking about arrays, we talk about chunks. When we're talking about data frames, we talk about partitions, right? We have multiple partitions within our data frame. Often, folks that we work with are already using like pre-partitioned file formats. Maybe you're using ZAR or Parquet or something that has some like inherent chunking inside of it. Dask can map directly onto those chunks so that it's like each Dask chunk is loading like an individual file, which is kind of nice for doing IO type stuff. So we have these Pandas data, like a Dask data frame made up of many Pandas data frames. And again, you can do all sorts of things in exactly the same way that you would in Pandas. And then finally, we've got Scikit-Learn, which is slightly more complex in the way that it handles things, but Dask has an implementation of Scikit-Learn, let's call it, called Dask ML, which follows the same APIs, and it tries to break the algorithms up into the individual pieces that we can build into like a big task graph and then execute on the scheduler. And you can have different Dask workers talking to the scheduler and taking different pieces of the calculation, swapping data around, and kind of parallelizing out our big computation. Now, like that works really well in some situations where you've got an algorithm that is very parallelizable. It works less well in other scenarios where there's going to be like a lot of inter-process communication, can get tricky. Kind of generally, we see performance benefits on most of the algorithms that you see in Scikit-Learn, but there are, of course, some things are going to perform better than others. So this is already like widely used in production. Many companies are already building stuff with Dask. So like one example that we like to talk about is Capital One. They've adopted Dask for doing much of their machine learning pipelines. So they're loading in large data sets from gigabyte up to terabyte scale. They're storing a lot of stuff in Parquet. Commonly, folks also store stuff in CSV. That's like a small like nod to GPU that I often like to make is it's not particularly intuitive, but GPUs are really useful hardware for converting CSVs into something more sensible like Parquet, because there's these horrible things that have to be done, like type inferencing on every single field that's really, really parallelizable. And so GPUs do that really well. So we have some customers who use like bits of RAPIDS to convert CSVs into Parquet, and then, you know, they might use CPUs for the rest of their workflow and use Dask. So they have Capital One tons of data in CSV Parquet with hundreds and thousands of columns. And they do all of their kind of ETL type work, data cleaning and feature selection, all that kind of stuff in Dask, because they've kind of come from a Pandas style workflow. And then they kind of can use Dask ML to do their training. Dask integrates nicely with XGBoost, and they see some really great performance speedups with that. We also, as I said, I come from like a geosciences background. So there's another community out there called Pangeo, which is kind of like a community of geoscientists who are trying to do their research and collaborating on like technical implementations. So folks within the Pangeo community contribute to projects like Dask and Zar and Numpy and all of those kind of things. They give talks at conferences to each other and kind of collaborate on how can we handle these like domain specific challenges and what tools can we leverage and what other tools do we need to build. And so, you know, we see folks in the kind of gigabyte to terabyte to even petabyte scale data processing, but they're very like array based rather than data frame based. They might have many, many terabytes or petabytes of data already stored in like an older format like HDF5 or NetCDF. They might want to convert over to Zar. And they want to be in that same world that a lot of data scientists are in, where they're working in Jupyter, they're doing like interactive computing with notebooks, doing stuff on their laptops, scaling out to larger systems. And so Dask is heavily used within that community to leverage their kind of work. There's another Python library called Xarray, which is built on top of Dask, and it adds axis labeling to arrays. So if you imagine you've got like an array of weather data, you might have like latitude, longitude, altitude, time. You've got like many dimensions, right? This big grid. And Xarray helps you kind of manage those dimensions because they have values, right? Like time has a value, and you might want to select a particular time range and those kind of things. Xarray helps you do those geospatial transformations and like index label-based transformations. I've just seen a question in the chat. So what are the requirements of data to be optimized and chunked by Dask? I mean, there's no like huge hard and fast requirements. Dask can load loads of different file formats like CSV, Parquet, Zar, just like whatever your data is kind of in, really, Dask can either load it or you can write your own custom loader for it. Obviously, if the data is already chunked, that's very helpful. If you're running Dask on like a cloud platform, you might have a load of data in S3. And so you can kind of leverage the parallelism of having chunked data, because each Dask worker will be pulling individual objects out of an object store, for example. But at the same time, if you just have like a giant CSV file, that's also fine. Dask will like read that in chunks. It will just do like regular file system reading, where you can just say, read in this large CSV file, but do it in 30 megabyte chunks or something. So each worker will like do like a byte range request on that file, or like seek through the file. Hopefully that answers your question. So as well as Dask kind of being able to work with all of these different libraries within the PyData ecosystem, it can also be deployed on a bunch of different systems. So there's like a whole like outer layer of tooling within Dask, which is just, how do I get a Dask cluster on a thing? That might be cloud platforms like AWS. We have like native integration with AWS, Google Cloud, Azure, Hetzner, DigitalOcean, whatever. It will like create VMs and automatically pull them together into a cluster. We have Kubernetes support. There's a few different flavors of Kubernetes support. Obviously, we're going to talk about the like latest iteration of that and how that fits with Kubeflow. Dask also runs really nicely on HPC systems. You might already have some large like scheduling system that uses Slurm or PBS or whatever to run on that. Dask is used within many national labs already. NASA uses Dask. It fits nicely into their system because it can just submit jobs into the HPC, and those jobs will pull together into a Dask cluster. We also have support for UCX, which is like a high performance network communication protocol. So if your supercomputer has some kind of more fancy or exotic networking like InfiniBand or something like that, NVLink, if you've got GPUs, Dask can actually communicate over those very performant links as well. So you can get some really nice additional performance benefits of your Dask workers being able to talk really, really fast to each other. And then Dask also supports, Hadoop Spark clusters. If you've got Yarn as your scheduler on Hadoop, you can Dask can submit to that as well. So you can kind of put Dask wherever you're already running, whatever your organization has chosen as their kind of platform to build on. Obviously, we're kind of focused on Kubernetes here in this talk. But at the same time, Dask works on a local machine, right? Like Dask is a super useful thing to use on a laptop, especially, my laptop's got 16 gig of RAM. Maybe I've got a 100 gig data set that I want to work with. Dask will just help chunking stuff in and out of my own RAM. It's also got 12 CPU cores or whatever. It will parallelize the work over all of those CPU cores. So I can leverage everything from my laptop, getting the best performance out of it in Python, all the way up to, I've got access to a nice supercomputer and I want to be able to run some big workload on that with hundreds or thousands of cores. And the API that we implement for all of this stuff feels the same, where you import a class and instantiate it. So in this example, we have local cluster. You import local cluster, you instantiate that, and that creates whatever resources you need. And that cluster object you can then use to scale things up and down and interact with the cluster and submit work to it. And so whether you're using local cluster, whether you're using Kube cluster or, AWS EC2 cluster, like whatever implementation you're using, the API feels pretty much the same. You're just launching on different systems. Dask also has some really nice kind of debugging tools, inspection tools, so you can see what's going on. This is like a reasonably old now, but this is a quick little GIF of the Dask dashboard. Each row in this dashboard, we'll get into all of this in more detail later, but each row in this is like one of the CPU cores in a worker, and each task that's being added to the end is like a Python function that's being executed. So you can kind of track what's going on, how much memory is being used. It'll give you like profile, flame graphs and everything of what's taking time. It's really useful for like digging into what is taking the time in your code that you're running. And so we have quite a big community these days. So we have many contributors, many active maintainers. It's used by a lot of folks. It's kind of hard. Like often at these things we say, we get this many pulls on PyPI and we get this many clones on GitHub and all that kind of stuff. Like those numbers are great, but also like lots of bots are downloading these things all the time for cache reasons and all sorts. So I don't like to use those numbers too much because I don't know if I entirely trust them. But we have a very active community. I think a number that we quite like is the fact that our documentation website gets 10,000 visitors a week. So we have like a big community. There's a lot of people engaging and contributing to Dask and building cool stuff with it. So another question in the chat is, what are the benefits of Dask over Spark/PySpark? One of the things that when I was working in research was we used Spark for some things, and particularly at the time, you're trying to use a Java-based system with Python. And so you're using this like compatibility layer, right, of PySpark. And so you'd be doing some work, something would go wrong, and you would get Java error messages, or you would have to go and debug stuff in Java, and it's just not as familiar. And so the fact that Dask is written in pure Python, it's kind of a native Python thing. You use Dask from within Python, kind of much easier to debug within that sense. The other big thing I think is the fact that it runs on my laptop and it runs on a cluster and it runs on a supercomputer. Right? Spark is much harder to scale down to those small use cases. You have to kind of jump into it with both feet on like a large workflow. The other thing is you can also use them both together. As I said, we have Yarn support, so you can schedule on those. So yeah, right. Another question is, how does Dask compare to similar tools like koalas? I can't comment. I don't actually know anything about koalas. I should probably look into it. So thanks for that. I will make a note to do that. If you have other, okay, sure, fine. There's lots of other like Pandas implementations. There's like Vakes, which is a reasonably popular one. The kind of core concept behind Dask is that at the center, it's a scalable Python kind of engine, right? It takes Python functions and converts them into a task graph, and then executes that task graph on a like clustered system. So that's kind of where the power is. It's like super flexible. We have then implemented data frames and arrays and machine learning on top of that kind of foundation. But you can also just pick up that foundation and build cool stuff with it. So Dask is not necessarily trying to be the best implementation of data frames. It's trying to be like a scalable framework that is a good implementation of data frames. I'm going to keep taking a few more questions, and then I'm going to keep pushing on. I might circle back to some questions in a bit. So there's a question about, I'm not so sure it's a question. Databricks implemented and is now part of Spark 3 as PyPandas. I mean, yeah, like there's a lot of cool stuff going on in the Spark community. Within Rapids as well, we support both Dask and Spark as kind of execution engines for doing like GPU workflow. Like there's a lot of cool stuff going on within the community. I think Dask is just really focused on this kind of being a core Python and PyData building block for building out other things. So there's another question about how's the comparison between Ray and Dask. So Ray and Dask are similar again. Ray is kind of up and coming more so than Dask. Dask has been around for slightly longer. There's like a ton of blog posts already out there comparing Ray and Dask. You can run Dask on Ray. They did a great blog post. Was it Anyscale, the company behind Ray? They did a great blog post about running Dask on Ray, and they have like a framework for Dask on Ray. So I don't want to get too into the weeds with that stuff, but there's like cool content already out there for having a look at those comparisons. A lot of these things are kind of intercompatible, as well as being competing technologies. So let's kind of shift off Dask a little bit onto Kubeflow and how Dask can be useful to you if you're using Kubeflow. So typical machine learning workflows that we see within, that folks are doing on Kubeflow is following along these lines, right? You're going to read some data, you're going to do some kind of smishing around and cleaning and preparation and that kind of stuff. You'll do some hyperparameter tuning and train your model, like your feature selection, all that kind of stuff. You got your big ETL chunk at the beginning, leading into training a model. You're going to have to score that model somehow, and then you keep going round and around that loop to try and get a really nice model. And then eventually, when you can prove that your model is going to be, better than what already exists, you then move into serving that model. And I've kind of put a bunch of logos at the bottom. Obviously, this is not exhaustive. You've all seen the Kubernetes diagrams of every single technology that you could ever use with Kubernetes ever. They're like vast. But to give you some like small examples here, it's pretty common to start at the beginning of this like ETL workflow, doing things interactively, doing things in notebooks, using Numpy, using Pandas, and kind of exploring the data, manipulating it, preparing it, and getting it ready for a state to hand off to something else. So you're going to hand off to hyperparameter, like optimizing libraries. You're going to hand off to machine learning libraries from like a data perspective. And then when you're doing scoring, maybe you come back to Numpy or whatever for doing that. And then there's other tools for serving those up. So what I'm going to focus on from the Dask perspective is this like beginning part of this workflow of the interactive. I'm in Jupyter, I'm in a notebook session, I'm using Pandas, I'm reading some data, I'm manipulating it, I'm getting ready to hand off to do some model training. So this is like a common thing that you might see a data scientist doing, working either in Jupyter Lab or maybe even directly within the Kubeflow dashboard with like the embedded Jupyter stuff, going through, loading in data, and kind of cleaning it up. Now the challenge around this is has historically not been the like computationally expensive step, right? Training the model is obviously the computationally expensive step. This is why libraries like PyTorch and TensorFlow and things have GPU support. They have clustering support. They have like all these kind of abilities to try and speed up that step because it can be painful. But as data is growing and people are trying to do more and more and more with their data, this initial ETL section is becoming larger and more cumbersome and slower. And so in a scenario where you're in Kubeflow using the notebook service, all of that stuff that you're doing with Pandas in the notebook is confined to that pod that Jupyter is running in. So whatever size you've kind of chosen in the notebook selector, you're kind of locked into that then. Even though you might then hand off to PyTorch, which is like running in a clustered mode where you have like many pods all working together to do some kind of distributed training. So Dask can be really useful in this like early stage of allowing you to break out of the confines of that notebook and leverage more of the Kubernetes cluster that Kubeflow is running in to do these other steps, but without sacrificing the kind of interactivity of being in a notebook and being able to explore and being able to do these things yourself. You don't have to switch from interactive to a pipeline in order to be able to scale out, although this stuff is super useful in pipelines too. So in order to enable all of this, we've got Dask tooling for Kubernetes, but we wanted to like refresh it and make it more robust. For like a small bit of history, some of the other implementations that we have speaks to the Kubernetes API directly, creates resources, and handles kind of adding and removing workers on quite a low level. And that's not ideal when things go wrong. Failure states are not particularly pleasant. And it requires a lot of permissions on the side of the user to be able to actually pull a Dask cluster together. So we wanted to follow the operator pattern in the new design. And so we have this service that you run on your cluster that can do all of that kind of messy stuff of creating pods and services and getting everything talking to each other. And then from a user perspective, we've created custom resources that they can then, create these like primitive objects of a, Dask cluster or a worker group or something like that. So the Dask operator is, a deployment that you run on Kubernetes, and you have these custom resources that you install that the user can then work with. And I've got like a little hierarchy diagram here just showing the like orange resources are the new custom resources that we added with the operator. And they, in turn, when you create those, they create pods and services and things in order to create the Dask cluster. So I don't expect any of you to like do any of this, but just to show, this is what the installation looks like for the operator. You just have to apply the manifests for the custom resources. You have to apply the manifest for the operator. And you also have to patch, there's a cluster role in Kubeflow, which defines what the user can do from within their notebook of, creating pods, creating services, using kube control, that kind of stuff. So you just have to patch that to add the new Dask resources into that list. Once you've installed everything and set that up, the users can then list Dask clusters, create them. I'm also just kind of showing here, making sure that the operator pod is ready. Once you've gone through and done all of this, I should have put a link on the slide, actually. If you go to kubernetes.dask.org, you'll find documentation for all of this, all of these commands, all that kind of stuff. I'm just going to throw it in the chat, actually. But if you go to kubernetes.dask.org, there's like way more material on this. Yeah. So then once you've got the operator installed, you can get into, go into Kubeflow, launch your Jupyter notebook. And this is just running in the default notebook environment that Kubeflow gives us. So I think it's like a SciPy based notebook or whatever that the Kubeflow sets up. And so in order to leverage this, we can do things purely in Python and not even worry too much about Kubernetes. So if we pip install the Dask Kubernetes package, we can import a cluster manager. So we have this new experimental cluster manager that uses the operator that we added recently. And in the same way, like I said about the local cluster, you can instantiate this kube cluster, and that will under the hood speak to the Kubernetes API, create custom resources, and kind of hook everything up. It does like a bunch of just quality of life, intelligent things. Like if you are in Kubeflow, it works out what the IP of the scheduler is and configures that so you can connect to it. If you're outside of Kubeflow, then it will check to see if there's any kind of ingress routes or anything configured, services set externally or node ports or something to kind of back out what the IP address should be. And if none of that is set, it will just shell out to kube control and do a port forward. So no matter kind of where you are or what you're doing, the cluster will be able to connect to the scheduler. As kind of useful if you just want to do things in Python. And then one of the features I'm super excited about is just this last little example on the left here, which is when I create a cluster with the Python class, I can also just go to kube control and list my clusters, and it will be there in a list, which sounds obvious, but we've not had that for a long time in the Dask community. The fact that the old way of doing this, it would create pods and services and things. I would be able to list those pods and services, but just having one resource that I can list and see and delete, most importantly, if I want to, if things go wrong, is just a really nice place for us to be at. The other neat thing we can do is to scale our cluster. So if you see on the left, we have like this fancy IPy widget thing that shows you the cluster status, and there's a little scaling tab. You can click that, and then there's like scale up, scale down buttons, which is kind of nice. Or you can just do it in Python. You can call cluster.scale and set the number of pods that you want to have within your cluster, and the operator will just add and remove pods as it needs. So you're still within this Python environment. You've just created a cluster that's kind of broken you out beyond the confines of your notebook, and now we can connect that and do some work, right? So if you import the distributed client, which is how Dask speaks to schedulers, you can then just do some work. So here's like a very small array example. I just chose this because this array is about 75 gig, which is much larger than the default. I think you get like half a gig by default, but it's probably larger than whatever the memory is of the notebook you're in. So if I did this in Numpy, I would get out of memory errors and things would blow up. But I can import this client, connect it to it. You can just pass it the cluster object, which is kind of neat. You can also pass it an address if you have like a long running cluster or something. And then I can run my work. And you can see at the bottom, just like a small snapshot of the dashboard showing my 5 pods, each taking on work. I'm running through that, the kind of task graph that's needed. So as well as doing all this in Python, you can do everything in YAML as well. These are kind of Kubernetes custom resources. They have been designed in a way where folks who operate clusters can kind of get involved. It's not like the Python writes the YAML and the YAML is unpleasant. We've tried to design the YAML in a way that looks familiar. It kind of nests existing resources like pod specs and server specs. So you can configure your cluster and you can kind of do whatever you want, whatever you need with it. We have a bunch of documentation on kind of how things need to be pulled together and how you can get stuff working. So we have 3 different types of resources in the operator. We have the Dask cluster, which is, you can either create manually or you can leverage with that kubecluster Python class. We also then have a Dask worker group. And this is kind of like a concept of each Dask worker is going to take functions and do stuff with them. And in most situations, you want them all to be the same. It doesn't matter which worker takes which function. They've all got the same amount of memory and the same libraries installed and that kind of stuff. But in some situations, you might want to say, I want 2 workers that have got GPUs, and then I want to annotate a couple of my functions to say, these functions should run on the GPU, so you can hand out to doing other things. Or maybe you have like a step in your workflow that the memory blows up and you need lots of memory. So maybe you're going to say, I want to have a couple of workers that have got double the RAM, and I'm just going to funnel everything through them at the kind of big expensive memory step. So when you create a Dask cluster, you get like a default worker group, but you can add more. You can create more resources and point them to the cluster with varying configurations. You can create yourself some heterogeneous clusters if you need to. And then the last resource that we have at the moment is a Dask job resource. This behaves a lot like a Kubernetes job resource, or if you've used the other Kubeflow operators, there's like a PyTorch job and a TensorFlow job or whatever. These are they're like a end-to-end execution of a container. So that container might be a notebook, or it might be a Python script that is doing some task. But when you create a Dask job, it also creates a Dask scheduler adjacent to it and sets up all of the configuration automatically. So if I just jump back a slide, here you can see the client. I've had to pass the cluster object. If you have the right environment variables set, you don't need to pass that cluster object. You can just create a client with no configuration, and it will just load the information from the environment variables. So when you run the Dask job, it creates the Dask cluster, and then it starts the user's pod and injects all of that configuration. So their pod can know nothing about how the cluster has been created. And that's really nice if you want to do a long training run or just a long processing run and submit it like a one-shot batch thing, but you want to have a Dask cluster besides so that you've got a good amount of resource available to that job. We're also going to keep adding more over the time. The other thing on our list that we've nearly finished is an autoscaler. So Dask can scale up and down, but the scheduler has a bunch of knowledge about what it wants. It would prefer to have this number of workers, or when it's idle, can say, I don't need any workers. So we're going to add another resource that will have the operator interrogate the scheduler and adjust the scaling numbers automatically. So just to kind of recap this little section, the new Dask operator allows you to create Dask clusters as native Kubernetes objects, either in Python or YAML. You can create multiple worker groups with different size and shape workers. You can run batch jobs with the Dask job resource. You can scale workers up and down. You can do everything with kubectl, or you can do it in Python. And you can quickly clean everything up in kind of different failure cases. Now, I've been talking for ages. This is a 2-hour session. I kind of want to give everybody like a little breather every now and then. So I'm going to put like a 5-minute break now. I'm kind of okay. So if folks want to ask more questions in the chat, I'm more happy to like chat there. I might kind of switch to talking in text rather than talking out loud for the next 5 minutes. But I'm going to set a little timer on my phone. If you all want to go and grab a coffee or something, take 5 minutes. And then when we come back, we're going to dive into the binder stuff. So I'm also just going to try and make sure my binder session is working. So head to this URL. It was put in the chat before. And yeah, see you in 5. Okay, that's 5 minutes. Hope everybody is okay. I'm back. So I'm now going to kind of switch speed a bit. I'm going to sit down on my standing desk. That's it. Virtual conferences. That's how it goes. Okay. So I'll start again. We're going to dive down. This is the like deep dive part of the session now, where we're going to actually dig down into like, how do I use Dask? Now that we've talked about some high level concepts of why Dask is useful and how we can run Dask on Kubeflow and use it within like MLOps workflows, let's actually just talk about, I'm going to write some Python and do some Dask. So I shared this link before a couple of times. Hopefully folks have managed to get this loaded up. What I'm going to do now, I'm going to like switch away from my slides. Oh, no, not time for a break yet. I'm going to switch away from my slides to, I've got this running here. So let me just pop over. So you should be able to see, let me make this much bigger. Okay. So it should drop you into like a Jupyter type session like this. And we're going to spend the next just over an hour running through the notebooks in this Jupyter session. So hopefully most of you have been able to get this up. Obviously, if you don't want to follow along, you can just watch what I'm doing. Please do shout in the chat if you're having trouble getting this started. So let's dive into notebook number 1 first. So this notebook it starts off with a lot of the things I've just talked about of like why Dask is great and why you should use Dask. So let's jump straight down to the let's see some code section. I'm just looking at the preview. Is this big enough for everyone? Shout in the chat if this isn't big enough and I will make it bigger. So the first thing we're going to do in basically every single one of these notebooks is create a Dask distributed client. Now, Dask doesn't actually need distributed to work, but we get some like nice quality of life things like the dashboard. I'm going to go one bigger. Hopefully that's okay. You get some nice quality of life things like the dashboard. You get the kind of profiling and all those kind of things. So we're going to be using distributed throughout this. Dask actually has like 3 different schedulers, I think, internally. You have distributed, which can run on multiple machines. You've kind of got the threaded one and the process-based one. I typically don't use the threaded or the process-based ones. So the way that we've got this set up here is I don't have any configuration options set in my environment or anything like that. So when I instantiate this client object, I can give it like some configuration options. And this will actually create a local cluster under the hood. So we're running this on Binder. Binder is, a small, it's given us like a small slice of compute thanks to some awesome sponsors of that platform. So you get like a couple of CPU cores and a couple of gig of RAM. So I'm just going to tell my cluster to kind of utilize everything that Binder's given us. So we'll see this little pattern. I'll use this over and over as we work through these notebooks. I've got this client. I'm going to create it with 2 workers and 2 threads per worker and 1 gig of RAM per worker. So once it spits that out, you should see we get these nice like little widgets. You can kind of expand them down and have a look. So we've got this client object. This client is connected to a local cluster object that has 2 workers. And then if we have a look at the scheduler info, we can kind of dig down. Oh, I have these 2 workers. I can see how much memory they've got and all sorts of other information. It's kind of helpful to see what's going on in your cluster. So when we create this client object, having this in the global namespace is enough for Dask to know to use it. We don't have to worry too much about clients and clusters and stuff anymore now. We can just use Dask and it will leverage that. And the other thing we can do before I actually start running some of this code is over on the left-hand side, you can see this environment has the Dask Jupyter Lab extension installed. And now this, like Dask has this dashboard that lets us see cool stuff going on. And one of the things the dashboard supports is like a nice integration into Jupyter. So I can click this little like find icon and it should just figure out, oh, I've got a Dask cluster in this notebook and I've got all these different plots available to me. So I'm going to open some plots just so we can see what's going on. I'm going to open the task stream and I'm going to open some other things. Let's have like the progress bars. Those are kind of useful. And let's get like maybe my memory. No, let's leave it at that for now. We can add some more over time. Feel free to play around with these yourself. So, okay, before I dig in, there's a quick chat in the conversation. How smart are the reader functions for big data? Is it able to do Spark-like predicate pushdown? So it does a lot of like graph pruning and it does kind of squashing the graph down. So we create this like large acyclic task graph. The reader will try and squash some stuff down. Some areas of Dask, so we have a library called Dask SQL, which behaves a lot like Spark SQL, and that does support predicate pushdown. There are other areas where we're like looking at adding that. But yeah, there's like a ton of optimizations and we're kind of always adding to those. So now that we have this client, let's load in some data. Now, like these are all just, if you look in the file explorer, there's like some data. These are all just like little CSVs from the like Kaggle open data sets or something. We have this data set called small beer. So let's have a look at what's in there. This is just a list of beers, basically, this CSV file. But you can see we read this with Dask data frame in the same way that we would normally read it with pandas, right? We used read CSV and we gave it the file path to the CSV file. But we also set a block size here, right? This is where I was saying Dask reads in chunks. And so we've said that it should read in chunks of, I think it's 12 megabytes, right? So Dask is going to take some chunks in from the CSV file. Now the CSV file is tiny, so there's actually only one chunk. And you can see when we inspect the data frame, as a result, it's created one task. We have a task graph with one task in it at the moment, which is just read the data. But it's important to note at this point, Dask like lazily evaluates everything. So nothing has happened here. All we've said to Dask is you should read this file to make this data frame. And it's gone and made a task graph and recorded that it needs to read that file in order to make that data frame. But it gives us like nice previews. It like looked at the header of the file and figured out what the columns would be called and worked out what the types of the columns are. So we can see this looks a bit like the Pandas, notebook preview, but it just doesn't have any data filled in. We just got some dots. So in order to actually get Dask to do stuff, we have to call .compute on something that is lazily evaluated. So what we could do is to have a look at our partitions, right? This is a data frame made up of multiple partitions. We can map a function over each partition if we want to. And so just to prove to you all that this is just Pandas under the hood, if I take the data frame and map type over each partition and then call compute on that, we should see that it just gives us back a list with just one Pandas data frame in there. We can also call head. Now there's a couple of things in Dask that call compute automatically. One of them is head, because like you're never going to want to lazily evaluate head. So I just call head. It will read the first partition and then do a head on that. If I had 1 million partitions, it would still take the same amount of time. It's only going to read one of those chunks in order to give us that. We can see the data in here. So, these are kind of beer names. I think we've got like the brewery information, some review data that each beer has been given, each beer's name and style and that kind of stuff. So let's do some data frame manipulation type things with it. So first off, we can do, we can just select all of the IPAs out of our data frame. So this should, if you've used Pandas, this should look very familiar, right? We take the beer style column, we do a string operation and check that the string contains the word IPA. We get this Boolean list of whether or not the column contains IPA, and then we're going to filter the data frame based on that Boolean list. And then we're going to call head on that. So we should just see the head of all of the IPAs in that list. And yes, we can kind of see here the beer name is over here. Each one of these has got IPA in beer style. So that's great. That was a lot like Pandas. But this is using this kind of distributed, lazily evaluated, scalable framework underneath. Now let's do the same thing, but just assign that to a variable. So we've got this variable now called IPA. And we can do kind of other normal data frame things. We could do a group by. We could group by the brewery name. We could grab the review overall column, and we could aggregate that. So if we have a look at that, we get this. I did this group by and this aggregation, and that returned immediately. Just to answer the question. So does beer style contains only the first chunk or all the chunks? It contains all of the chunks. But this is kind of what I was saying. Dask is doing an optimization here, right? When we call head, it knows it only needs one chunk, so it doesn't bother reading the rest of the chunks. So I've now got this mean IPA review data frame, and if I just have a quick inspect of that in Jupyter, we can see now that the resulting data frame has a mean column and a count column. We still don't know what's inside it because we haven't calculated it yet. But we can also see that our task graph is growing. Our graph is now at 7 tasks because we've done a filter and a select and those kind of things. Question is, what is the way to see a specific chunk? That's a good question. I think you can do partitions. Yeah, I can do partitions. What is that? Partitions is a property. Yeah, so I can do like partitions 0, and that gives me that. And I think I have to compute that. That gives me the first partition. I guess there's only one partition in here. So, but yeah, you can select a specific partition. So, as I said, we now have this data frame with 7 tasks, and if we want to actually see what the mean review is we have to call this compute manually. So then you can see, that these have been calculated for us. And then maybe we want to take the 20 largest from the mean column. So again, these are all kind of regular Pandas-y type operations. We can see, these are the best rated beers. Obviously, some of these have just got 1 5-star review. But looking down here, like, that brewing company has got an average star rating of 4.5 stars with 466 reviews. All right, so these are all kind of data frame manipulation type things, but we've done it in a distributed fashion. And to kind of show one of the nice things about that is reading a chunked file is one thing, but then you also have to think about, how do I write to disk? If I've got all of these workers that have data, how do I kind of funnel that back into writing to a file system? So one of the ways that we can do that is we can just use wildcards directly in the file name. And so I can say, I want to write this data frame to a CSV, and the file name should be this. And each partition will get written to disk with, 0 and 1 and 2 and whatever index in the file name. So if I just write this out, there was only one partition in this one. So you can see it's created this IPA-0.csv file. But it means that all the workers can get data to disk. Obviously, if you're using a file format like Parquet, that is like natively chunked, and it will do all of the partitioning. Like each Dask partition would write to a Parquet partition. Yeah, so there's a little bit of history about Dask in there that you might want to read later because it's not stuff I hugely covered before. So let me just check where I'm at with timing. We've got an hour to go. We're kind of 10 minutes into this block. I'm running slightly behind because I waffle a little bit. With no wildcard, will Dask save all chunks in a single file? Yes, it will. So one worker will aggregate everything into a single CSV. So what I'm going to do now is I'm going to give you 5 minutes to work through this lab exercise. Just a little hint there is the solution is the next notebook. Please don't peek. Give it a go. See if you can write things. There's lots of hints throughout. But this will walk through loading in a different file and doing some kind of data frame style operations on it. So I'm going to give it 5 minutes. Again, I'm more than happy to answer more questions in the chat. I'm going to kind of reassess where I'm at with my timings quickly. And then we'll go through the solution in 5 minutes. Okay, that's 5 minutes to work through that. Hopefully I've unmuted successfully this time. So I'm going to work through the solution to this notebook, and then we'll move on to the next section. I want to just quickly read what's in this one. That's fine. Okay. So this is the same notebook as the lab, but it's just got everything kind of filled out. So let me just, I've got like a bunch of notebooks running now. So I just want to make sure I've only got the right one running. Otherwise my Dask clusters might tread on each other's toes. I'll just stop everything. You can see I just stopped a notebook kernel. We just stopped the Dask cluster that was running in it, and my dashboard pages have just kind of fallen back to, they've fallen back to the old Dask logo. We should update. We need to update these actually. We changed our logo this week. So the slides and this may be a little out of sync. But if I create the Dask cluster again, those plots should repopulate. There we go. Great. So in this was reading in the page views small CSV file. Now the little trick here is that was a space separated file rather than a comma separated file. So just like in Pandas, you have to specify what the separator is. And again, we set the block size. So you can see with this one loading in this file, the CSV is big enough that it's going to take 3 tasks to do the data loading in from that file. The next thing was to rename some columns. So again, just like Pandas, you can assign the columns property list of column names. We can do drop to drop one column. So we just end up with project, page, and requests. And then we can filter the project looking for how many, to have a new data frame with just how many English articles there were in that data set. You can see we're slowly building up these 18 tasks. And now what we can do is we can call compute to see how many articles we have. So we can do a count and then compute to see how many articles are there in the whole project. No, my dashboards aren't showing anything. I've noticed Binder doing this being a bit weird lately and not showing actual graphs. There we go. You can see my progress bars and stuff now. I just had to refresh those plots because they've gone a bit funny. But you can see we can count the total number of articles in each of these data frames. Now, one of the questions in the chat was, can I like Pandas load stuff into memory, right? And then everything's in memory and that's nice and fast. Loading the data is slow and then doing stuff with the data can be fast. But obviously, if you don't have enough memory, you're kind of done. One of the things you can do with Dask is you can persist data in memory. Now, this does assume that you have enough memory to hold all of the data. But in this case, we do. So I'll just show you, instead of calling compute, we could do something like we could say ddf2 equals ddf2.persist. And this will compute the graph up to that point and then stop. And you can see that our progress bar is still there. It hasn't gone away like it did before. So this graph is like paused at this point now. ddf2 is like materialized in memory. And then anything we do with ddf2 in the future, like this group by, will kind of continue from that checkpoint. It won't read the file anymore. So if I then do this last thing, which is to do like a record count across English, French, Chinese, and Polish, I can do that. You can see it did that computation, and you can see the other progress bars fill in. It gave us the results, and then all that stuff in memory, all those futures kind of evaporated, but we're still left with our persisted point. So hopefully that's helpful. One of the things we tend to find folks do is like, you load some data, you do like your first cut of the data, and then persist that in memory. Mainly, you know, if the data set is like a terabyte, but you actually only want a few hundred gigabyte of it, and you've got a few good machines in your cluster, then you could persist a subset. I'm going to close out that Dask cluster so that the dashboard's reset. So that's going through that lab solution. We've also got like another. I don't know why that's open there. We've got another exercise here, notebook 4, if you're following along. This is doing pretty much exactly the same thing again, but we're going to dig down into the graphs. Another chat, is there any way to log performance of tasks in production? So in a minute, like the next little section I'm going to show you is like profiling your code and how you can kind of get information out. Dask has like an eventing system that you can record checkpoints in as well. it does expose some Prometheus metrics. One of the things that's like on my to-do list is like exposing the whole event system so that you can see kind of checkpoints in other monitoring systems, whether it like pushes those into Influx or some other kind of system. So as like an individual, you can inspect the performance of your code, but in like at like a production scale, from like an observability point of view, there's a lot of work in progress there. So let's run through this last data frame style notebook. I'm going to start another Dask cluster. This time we're going to have a bit of a look at what's going on with these task graphs that we created. So we're just going to read in these page views and just do like a bunch of things we've done already, like rename the columns and all that kind of stuff. So we get our data frame with 18 tasks. We can count those, and we should be able to see. My task cluster, the dashboard's not appeared. We can count those and see how many records there are. But one thing we can also do, instead of computing the result, we can call visualize, and this uses GraphViz to show us what that graph actually looks like. So we can see at the bottom we have 3 calls to read CSV to chunk through our data. We have 3 calls to a rename function with data moving between. It's going to drop that column. So we've got this drop by shallow copy call. These are kind of all internal pandas calls that are happening within Dask, but they're happening multiple times, chunked over the data. And then we're going to do that count. So each data frame is going to call count, and then it's going to aggregate those up to add all of those together to give us our final result at the top. And that gives us our answer. So it's great to see kind of what's going to happen before you actually do it. If we want to do an English only count, if we visualize that, we can see there's like an extra filtering step here where we've got this, after we drop the column and we get our kind of intermediate step, we want to check whether or not the language is English. So we have to like get that item, check whether it's equal, and then do it like a select on that. So you can see all the different steps that kind of go into performing this calculation. Now, the other nice thing that we can do is see all of this in the Dask dashboard as well. So what I want to do is I'm just going to do this persist call again. PDF 3 equals that dot persist. I run that. I don't know why these little iframes are not happy. Right, we can see these tasks executed here. But let's actually open this dashboard. I'm going to cheat a little bit. I'm just going to say open this frame in a new tab because I know that I can do that. And then I'm going to go to the status page. Now, this is like I'm doing this because this is like a weird binder thing. But when you start a Dask scheduler, it runs a dashboard on port 8787. And it looks like this. It has a bunch of plots that you can see, and you can kind of drill into those. Now, the Jupyter Lab extension is kind of calling into that and showing individual plots, and you can move them around, and that's great. But maybe if you're not in Jupyter, or you want to just kind of find out about your Dask cluster in other situations, you can just access the dashboard directly. Now, this kind of gets proxied by binder, so I just knew where it was. But yeah, as I say, if you run the Dask scheduler locally, you run local cluster, just go to localhost 8787, you'll get this web page. So we can see this is the general status. It shows us how much data is in memory, how much data per worker we have, our task stream, our progress bars, all that kind of stuff. We can click into the workers tab and we can see how many workers we have. So we have our 2 Dask workers that we created and kind of information, we gave them each 1 gig of RAM, these obviously rounded a little bit. We can get information about the scheduler system itself, how much resource is being used by the scheduler, how much of the machine. So in some deployments, you might end up with the scheduler on 1 dedicated node. Sometimes you might have it co-located with other things. So it's useful to check kind of how resources are going. On the profile page, this is like what I think is one of the most useful pages, is of this code that we've persisted, we can see all of our function calls as a flame graph. So we can see like our overall workflow and kind of go up through and say, oh, this is the read CSV call here. So this is taking like a big chunk of time. And what's happening before that? Oh, this is another read CSV. And then we've got all of our kind of take and drop and all these kind of other calls here. So we can see, oh, our IO is the thing that's slowing us down, which, is pretty normal. But this is just a great way to come in and debug your code and see everything that's going on. And you get this for free just by using Dask, basically. You can also use the graph page. to kind of have a look at that graph in this sense. So, this graph was like a vertical one like this. On this page, it just kind of shows each of those tasks, but it doesn't show the function calls. It shows the like intermediate memory points, and you can see, oh, these were calculated and then they have now been released. So that memory's been freed up, but this one has been calculated and is held in memory. They're gray when they've not been calculated yet in the future. And this page can be useful as well to see where things are at. We also have like a task groups page, which kind of groups things a bit more and shows, here's one pandas call and here's another pandas call. And this is the count, and this is this is the count that happens on each partition, and then this is the aggregated count here. And there's tons of different plots that you can see going on in here. If you've got GPUs, you can see GPU memory and all those kind of things. So what I'm going to do is, we've got 45 minutes left. I'm going to take like another 5-minute pause. I've got like a couple more sections I want to get through. We can talk about arrays, machine learning, and dig down in some like Dask stuff. I am running slightly behind on time. I think I'm spending too much time answering questions and chatting with you all, but thank you. It's always nice when there's like back and forth, especially in these virtual things. It's weird kind of broadcasting into like a room of people that you can't see. So thank you all for the chat that's going on. So what I'm going to do is I'm just going to swap back to the slides and go back to this quick break thing. I'll set another 5-minute timer, and then we'll move on and talk a bit about Dask array and do a little bit of machine learning stuff as well. So again, feel free to ask more questions in the chat, and see you in 5. Okay, that's 5 minutes. Hope you all had a good break. Let's keep going. So I'm going to come in and just close out my Dask cluster and move on to the next notebook. So we've got like a few sections here. We've got 40 minutes to kind of go through these. I'm going to go reasonably fast over some of these. So if folks like, so the topic we're going to talk about is like NumPy style arrays. We're going to talk about some scikit-learn style machine learning. We're going to talk about like bags and futures, so constructing your own kind of primitives within Dask. And then distributed, which will be pretty quick because we covered a lot of that at the beginning. If any of those topics are like particularly interesting or exciting to you, please feel free to say in the chat so I can like adjust my timings accordingly. But let's open up notebook number 5, which is the array notebook, and we'll get started on that one. So Dask array is very much like the data frame, but for NumPy. And so instead of having partitions within like a row-based data model, NumPy arrays can be any number of dimensions and shapes and sizes and whatever. So in order to do that, we have like a Dask array, which is made up of many NumPy arrays, and we tend to have like a chunking scheme that decides on how big those partitions are. So again, let's make ourselves a nice little Dask cluster, and we'll get these plots alive again so that we can see what's going on. Okay, they're refreshing. So you can import NumPy and you can import Dask array, and they behave pretty much exactly the same. So if I do like in NumPy, I can arrange the numbers 0 to 50 with an interval of 3. I can do exactly the same in Dask array range, but I can say how many chunks I want. Now, in this example, I'm saying this chunks means chunk size. I want them in chunks of 5. So we actually end up with 4 chunks over our array. Our array is 17 items long, so it has a shape of 17. And the chunk size is 5, so we end up with a chunk of 3, a chunk of 3, and then a chunk of 2. Now I can have a look at the kind of standard NumPy information, like what is the D type of this array, what is the shape of the array, but I can also get the chunks and the chunk size. So I can get like a full list of what chunks exist and how big are they, and then I can also just get how many chunks are there in each dimension. So this is just a one-dimensional array at the moment, so we just have one item in here. And we can also do visualize like we did in data frame, so we can just see we're going to do 4 separate A-range calls that results in 4 separate chunks of data in memory. And then we could say, well, I want to double every item in my array, and we can visualize what that looks like. And so same kind of operation, go through the A-range, and then we're going to call power on each of those in NumPy. And we can compute that result. And my graphs are not working again. Yeah, we can compute that and we can see those answers. And we can also like check the type of these. So if we compute that result and have a look at what the type is, you can see this result that comes back, the return type of compute here in this example is a NumPy array. So everything is NumPy kind of everywhere when using Dask array. The workers are kind of speaking NumPy to each other and then aggregating together results that come back to you in the notebook and NumPy. So it's much like everything is pandas in the data frame examples. Now, you can swap out these internals. If something is NumPy-like or pandas-like, you can just literally swap these. Dask will still work with them. Dask just likes things that are like that. So in the GPU world, in the stuff that I do at NVIDIA, we tend to use cuDF for data frames, which is like a GPU-accelerated data frame library that follows the Pandas API, or we use CuPy, which is the same for arrays. You can do all the kind of standard arithmetic stuff that you would do in NumPy. You can multiply things, you can sum them, you can do whatever you like to do typically in NumPy, you can do in Dask array. Let's just quickly have a look at some blocked algorithms. So if we just create like a random array, again, this is a random array with a chunk size of 5. We can sum the items in our array, and you can see that the result come back here. We haven't called compute. So the result that comes back is another Dask array. It doesn't have a shape or a chunk size because it's just a single integer value. And we can have a look at what that would look like. So we can see we do our random sample, we sum things together, and then we have like an aggregate step again to pull things back, and we get our final result at the top. And so we can call compute on that, and we get a random number. We can also do the same kind of thing and do some kind of more complex operations, like maybe we want to transpose our data and add it together and those kind of things. So let's make a slightly larger array. I'm going to make a 2-dimensional array with a 2-dimensional chunk size. So you can see this is a 15 by 15 array with chunks of 10 by 5. So we end up with like 3 whole chunks and a few partial chunks again. And then we can do something like take our array and add it to its transpose and then do a sum of that whole array. And if we have a look, again, that results in like one single number. And if we visualize that, like transpose is a much more complex operation. So you end up with a much more complex graph of what Dask is going to do underneath. So we still have our 3 random samples along the bottom, but then there's a lot more going on in here to do everything that we've done. But that's fine. Dask has created this graph. We can submit that to the scheduler, and it will compute the result for us. And then the last thing I want to show in this, I don't know why my graphs are dead again. These graphs use WebSockets underneath, and I think the WebSocket just dies after a little while. Let's make a really big array. So this isn't really big, but like in Binder, we have 2 gig of RAM. Remember from the beginning, we have 2 Dask workers, each has 1 gig of memory. We have 2 gig of memory total. So I just made an array here that is 3 gig. So if I tried to do this in NumPy, it would fail. It would give me an out of memory error because I have 2 gig of RAM, 3 gig of data, and I'm stuck. But if I want to do this complex operation, like adding it to its transpose and doing a sum, it doesn't matter that this is larger than memory because we have lots of chunks. Dask would just start working through each one of these operations, kind of creating memory, freeing memory, swapping stuff around. You can see there's some kind of red lines in the graph at the bottom. This is when the 2 workers are communicating with each other, passing memory back and forth. Typically, you want that graph to like not be red. If that graph is really red, that means that you're getting like bottlenecked on your network because all your workers are talking to each other a lot. Typically, at the end of a calculation, there's more communication than at the beginning. But you can see we kind of chunked our way through this larger than memory array. And we're able to do the operation. We didn't blow up. We didn't get any out of memory errors or anything. So this is kind of one of the like compelling things that Dask can do, even on a small machine with 2 gig of RAM, is you can just work with larger than memory data sets. So let's close out that cluster. Now, I think what I'm going to do to like claw a bit of time back is I'm going to work through. There's a machine learning example here, and then there's like a machine learning lab, and I think I'm going to skip the lab, but because that's kind of something you can come back and do in your own time if you want to. So there is like things like at the very end of this, there's like a optional hands-on lab, and there is a solution notebook afterwards. But let's talk a bit about DaskML and how we do machine learning tasks. So DaskML behaves a lot like scikit-learn. It has a lot of the same classes. It has a lot of the same features. And so you can do kind of simple machine learning tasks in Dask as well. So scikit-learn has like a bunch of tooling in it for doing some parallelism. And you can just put Dask in there as like the joblib backend for scikit-learn, or you can use DaskML directly. So in these examples, we're going to use DaskML directly. So maybe you want to do something like a logistic regression. Yeah, so let's do it rather than me waffling around the subject. So I'm going to create another Dask cluster again, same shape and size as we have done all the way through. I was going to answer a quick question from the chat. I'm not sure if this was asked, but is there a guideline on how to choose the number of chunks for your Dask array? I mean, in those examples, I was like making up Dask arrays of random data. So I was just arbitrarily choosing the chunk sizes. In reality, your chunk sizes are going to be dictated by the data that you already have. And you might want to think about rechunking that. There's like all sorts of different reasons why you might want to choose different chunk sizes. Like if your data is in an object store like S3 on AWS, reading files that are around 50 megabytes is like the optimal file size for like the trade-off between the HTTP overhead and the like throughput of S3. So having 50 megabyte chunks in like a ZAR array, or some kind of array format on S3 is like a really nice chunk size to choose. You might have other reasons why you want larger and smaller chunks. There might be like domain specific reasons, like if you have like time series data, you might want to have like chunks that contain an entire day or something like that. There's lots that go in. I think, let me just have a quick look on the Dask blog. I'm pretty sure somebody contributed a really nice post on chunk sizes, choosing good chunk sizes in Dask. Yeah, I'm going to put this in the chat. This is written by a scientist. I think she works in like biology and does a lot with like image processing. So have a read of that. It's a great post. So I've got my Dask array here. Now in this machine learning example, what we're going to do is read in this diamonds data set. Right, this is like a dummy example data set from Kaggle. Again, this has got like a bunch of information about a load of diamonds, right? The carat and the cut and color and clarity and all the kind of things you care about. And then the price, the value of that diamond. What we're going to try and do is just like a little bit of simple machine learning where let's just rename that column. We're going to call categorize, which is something you can do in scikit-learn, and reshape our data so that we get our kind of categorized additional columns in here. And then what we basically want to do is train a model that can, based on the attributes of the diamond, predict how valuable that diamond is. So we have our data set, and we're going to need to split this out into our information about the diamonds and then our information about the price of the diamonds. So now that we've kind of got our data frame in the shape that we want and we categorized it and everything, we're now going to switch to Dask array because like all the machine learning stuff wants arrays rather than data frames to work with in here. So we can convert our data frames directly to arrays. We've gone from this prepared data frame to this Y. It's not a particularly good variable name, but this Y array that is the same shape and size. So you can see this was a data frame at one point. It was like a one high and a very long thing. And we're going to drop the price column from the other array. We're going to drop the price column from the data frame and then get an array from that. So we have one array which has got all of the prices in, and we've got one array that's got all the other data in it. We can then do our train test split like you would do in scikit-learn. You can import this from DaskML. I think you could also import this from scikit-learn and it would work. But we're going to split this out. So we have a training data set and a testing data set. I think it's just going to, we're just going to save 10% of our data for testing with. We can have a look and see, we now have some slightly smaller arrays that have been broken up for doing training and testing. And then from DaskML, we're going to import this linear regression. So again, this follows the same API as SciKit-Learn. This is I assume you've like gathered the theme throughout me giving this talk of like, these follow the same APIs, right? So if you know how to do a linear regression in SciKit-Learn, the keyword arguments are the same. We say what kind of solver we want. We always say how many iterations we want to do. I'm just going to refresh my frames because the WebSocket's probably dead again. And then I'm going to train my model. If I do fit. Now we can see the way that DaskML is doing this particular operation is it is creating a Dask graph for each training, but not one overall graph for the whole thing. So we've specified 10 iterations. It's going to submit 10 graphs. So you can kind of see these progress bars resetting and then going through as they go through each iteration. We can see our progress down at the bottom as all of our tasks are being calculated. So that's going through. There's a question in the chat. Sorry, I think I missed it. Can I use any ML library or are they supported by DaskML? So DaskML is intended to be like a scikit-learn replacement. So the naming is like not particularly ideal because it feels like it covers all of ML in Dask. But like it does have like various bits and pieces. Yeah, somebody else has just linked the Keras stuff as well. Like it provides some integration with other libraries and it provides like a drop-in replacement for scikit-learn. You can also use other libraries that already support it. So if you use XGBoost, which is super popular, XGBoost actually has native support for Dask. So you can import like XGBoost.dask and use their like support they've built on top of our primitives to give XGBoost this kind of distributed thing. There's a bunch of nice examples out there. Another like common workflow, if you want to do like deep learning, then you could do all of your ETL within Dask and then hand that data off to PyTorch or TensorFlow or whatever. And we have some utility stuff for doing that. What's really nice is when you get in a situation where you have maybe a Dask cluster with 5 workers and if you use the XGBoost integration, XGBoost will speak to the Dask scheduler, ask how many workers it has. It will then speak to each worker and start an XGBoost worker on each one of those. It will just like sub-process it on the Dask process. Those will like do their communication through Rabbit or however it does that. And then it will ask for the like pointers to the arrays and Dask will hand the pointers over. And then you effectively end up with like an XGBoost cluster sitting on top of your Dask cluster. And then XGBoost does its thing and hands the results back and then shuts down and you still end up with your Dask cluster. So you can kind of use Dask as a platform for running other things. And we can do that, you could set up like a 5-worker PyTorch cluster or something and hand the data across in the same kind of way. And we can do that with the GPU stuff as well. If you have like CuPy-backed GPU arrays, there's a nice new-ish protocol called CUDA array interface that allows you to pass GPU memory pointers from one library like Dask to another library like PyTorch without doing any copying, which is really neat. So there's another question. What is the performance gain of Dask linear regression or similar models versus scikit-learn? Given that you can't really parallelize the algorithm, is there any way to at least parallelize grid search using Dask? So I'm not like a machine learning like expert. I'm more of like a Dask distributed deployment clustery kind of person. All I kind of know is kind of what I said earlier on, in that some algorithms make sense to be distributed, some algorithms don't. We try and whatever we can do, we do. So some things go like much faster than others. In Rapids, we have some great graphs. I should try and find some of those of like, oh, this algorithm is 2 times faster, this algorithm is 10 times faster, this algorithm is 10,000 times faster, depending on how parallel it is. The other thing that we can do in Dask is like it is doing tasks like independently of each other. So all the data loading and stuff is being parallelized. But in this particular like example of this linear regression, some parallelism is happening, but I don't know the details of exactly what's happening there. And then, yeah, so just to kind of round off this notebook, you can have a look at the results of the training and see how good it is and calculate your mean squared error and all the kind of stuff that you would want to do. So that's kind of the scikit-learn piece. Please, if you are interested in that, go ahead and have a look at the lab after the talk. We've got 20 minutes left. I'm going to take like maybe a 2-minute break just to get a drink for myself quickly, and then we're going to go into the like bags and futures, like Dask fundamentals stuff, and then kind of talk a bit about distributed and wrap up. But if you do want to run through this, there's another example here that's using power plant data based on the properties of the power plant, right? Temperature and ambient pressure and all that kind of stuff, and you train a model to calculate the energy output. So it's very similar to this example with the diamonds, but using power data instead. So, okay, I'm going to take 2 minutes. Let's pop back to this slide just for that and take 2 minutes to get a drink, and then I'll come back and we'll carry on. Again, if you have more questions, please feel free to throw them in the chat. Okay, that was a quick last little break there. I'm going to move on to the kind of last bit of this tutorial material. Spend 15 minutes or so talking about some of the kind of lower level things within Dask. So there's 2 pieces in this notebook. The first one I'm going to go over reasonably quickly because I don't want to get too into it, but we do have a concept within Dask for like a looser collection of items. So rather than anything as formal as data frames or arrays or whatever, we do have this idea of a bag, which is effectively like a sequence of items. It's a bit like a list or something in Python, but it's distributed across. And so often the like time that I've used this is maybe I have something like a list of file names and I need to, load something out of each file before I can kind of aggregate them together into some of the like higher level objects. But just to show you a little example of how this works, let's import Dask bag, and you can create a Dask bag from any kind of iterable in Python. So we'll create a do from sequence, and we'll just give it a range. And again, you specify n partitions. Now this, unlike in the array, this is not how big each partition is, but this is how many partitions there should be. So there is a slight inconsistency in the API here. But in bag, we can see here, oh, we've got this sequence of items and there are 4 partitions there. So we can kind of compute those to see how many items there are. We can compute the count on that. We can also do, n partitions to double check that there's 4. And we can do all kind of standard operations on it, right? We can map a function over it. So we can map a lambda function over each item in our bag. We end up with another bag. So this is just everything in our bag squared. Again, it just shows us this is our 4 partitions. And this, as with the other things, is building up this task graph. Now I can do something like take 5 items from the bag. I don't think order is guaranteed here. Most of the time, this example does show us the first few items, but order, yeah. No, okay, oh, good. Okay, it's taken 5 items, but order is not guaranteed. So it's given us some various items from that bag. No, that is, isn't it? Because I've squared it. So that is giving us the correct order, but you shouldn't depend on that. We can also do things like group bys on this. And yeah, so yeah, here's a little note. Remember, bags aren't ordered, so you may or may not see the output in ascending sequence. Now, I'm going to kind of finish up with bag stuff there. It's basically just an iterable that you can distribute, which is useful in a bunch of situations. But let's dig now into Dask delayed and the futures API. We have like a couple of different ways of dealing with Dask's like low-level primitives, and we're going to cover both of them here. So we're going to start off talking about delayed. Now, this is kind of what Dask is doing right down at the like function level of how it is breaking all of this stuff up into task graphs, and we use this to build everything else. So all the APIs that we've seen so far. So let's talk a little bit about what that looks like. Let's say I'm going to run some Python code on my single-threaded machine. Python just uses one thread, one call to do its stuff. And I've got a few functions here. I've got an increment function. Oh, where's it gone? I've got an increment function, a double function, and an add function. Now, to kind of simulate that these are like more complicated than I'm making them out to be, I've got some sleeps in here. So each one of these functions is going to take half a second to execute, even though they are just adding and doubling and adding stuff together. So if I define all of my functions and then do something with them, So I've got some data in a Python list, just the numbers 1, 2, 3, 4. I've got an output list here that's empty at the moment. And if I iterate over my data list and I increment the number, I double the number, and then I add those two things together, right? The incremented one and the doubled one, and then append those to the output array. I could then sum that output array. So this is, this is a toy example, but I'm just building up some kind of little workflow of piecing together some data manipulation here. And I've got this little Python magic here that's going to time how long this cell is going to take to run. So given that we've got these half-second sleeps in here, we've got 4 items in our list, we're going to do 3 function calls on each one, and then a final function call. All of that time added up gives us 6 seconds. It takes us 6 seconds to run all the way through all of our function calls here. But we have 2 cores in this Dask cluster, right, in our machine. And if we use Dask, we can use both of those. So let's show how we can do that. We can do that at this low level with Dask delayed. And Dask delayed is a decorator. We can use it as a decorator. You can use it manually here as well. So if we create a new function called lazy increment, we just call delayed on increment, and we end up with this like lazy version of increment. And we can try it out. Let's call lazy increment on 3. Right, so we're expecting the result to be 4, and it will take half a second. If I do this lazy increment, it returns it immediately, and it gives me back this like delayed thing. This is the ID of this function call that the Dask scheduler knows about. So we've got this delayed object, and we can visualize it just like we did with anything else. So all we've done is we've taken some data and incremented it, and it's going to give us some data out. And then we can also call compute, just like we do with the other APIs. So this will actually ask the scheduler to take this delayed function call and execute it. I think these plots are gone again. Would have flickered something, I reckon, for a second, but I'm going to compute it again, see if anything comes up. Yes. Okay. I just saw a little increment there. Yeah, you can see if I hover over it, it says inc down in the corner. So that ran on our Dask cluster. It's just our simple Python function that we've made lazy with delayed. And we can do it again. We can call it on itself when it's not being computed, right? We've got this delayed object, this inc output, and we can just call lazy inc again on inc output. So if I do that and then visualize, you can see we're starting to chain function calls together in a graph. So this is our kind of uncomputed graph that Dask knows about, and then we can call compute on that. So it'll call inc twice. Maybe saw a very brief bit of information in the progress bar then as it was running through that. So now that we know how to make a function and make it lazy and call it with Dask, we can go back and convert our other example. So if we have our old inc double and delayed functions, we're going to just inc double and add. We're going to redefine those here and make them all delayed with the decorator. This means that those will be evaluated lazily. And then we've got the same code example here with data and our output array and doing all of our stuff to it. And you can see we can even make built-in Python functions like sum a delayed function. Okay, we can't decorate it because we can't define it, but we can call delayed on sum to turn it into a lazy sum. And if I run this, based on the fact that we've got 2 workers, how fast do you think this is going to run? It's actually going to run instantly because we're not actually computing the result. All we're doing is building this graph, right? We're just saying to Dask, this is what this computation looks like. All of these function calls, it looks like normal Python, but because everything is lazy, this total ends up being this like future object, this delayed object. And if I call visualize, we can see our more kind of interesting graph going on here. We've got our doubles and increments treeing up into the intermediate results, which tree up into all of our additions, which tree up into a sum. All right, so we get our Dask graph, and then we can call compute to see how long this will actually take. If we compute this graph, my progress bar's died again, but you can see we have 2 Dask workers, so this took 3 seconds. So we've halved the computation time that we would have done before. Now, obviously that makes sense because the shape of this graph can be easily broken up by 2 workers. Okay, there's a question in the chat. Would this work if the output of one function depends on the run of a previous function? Yeah, you would just draw the dependencies in, extra lines between different steps. If you remember in the like array one, if you looked at some of the graphs down in here, there's like some very complex sets of dependencies where you can see lines kind of going everywhere of this depends on that, depends on that. It knows what all of its dependencies are. So that's how we can do delayed. This is how we can kind of create lazy functions. And the other API, this is a separate API that we have within Dask, and this follows the concurrent futures API. So if you're familiar with that kind of Python concept, we can create futures directly by submitting functions to the scheduler. So instead of saying this is lazy and then calling it and the scheduler doing some stuff, we're going to kind of explicitly say to the scheduler, here's a function, can you do this for me? And it will run it immediately, but it will return to you immediately while the scheduler is busy. And it will give you a future that follows the current futures API. So let's define a new function. We'll call it inc again. And this is just going to sleep randomly, this one. And we can use our client object. Remember, like we've been making this client object in every notebook, but we've just been relying on its like presence for Dask to know what to do. But we can use it directly and tell it to do things. And one of the things we can do is submit. So we can submit a function call to the scheduler. So you give it like the function and you give it the arguments that should be passed to that function. And if we submit inc, we immediately get back this future that's in a pending state. And we get the key like we had in delayed. But the scheduler is off busy doing this, but it's returned to us. We've got our notebook back. We can carry on doing stuff while the scheduler is busy. And we can check the type of it and see that, oh, this is a distributed client future. Now, in the time I've been talking, the scheduler will have finished doing this. So if I print F again, we can now see it's still a future, but it's finished now. The client has spoken to the scheduler and the scheduler has said that this is done. I have the result. It is in memory and it's ready to give you. I don't know whether these will show. Yes. Sorry, these plots keep dying again. But you can see the result of this increment is sat on the scheduler. The progress bar is here. It is finished. It's waiting for us to do something. And so we can ask for that result directly. We can do f.result, and the scheduler will pass that to the client, and we can see it in our notebook. But that memory is tied up on a worker, right? The scheduler is holding this future for us. This is kind of what happened with persist that we talked about earlier, is that the scheduler kept a reference to one of the futures, so everything kind of stays there. But we can delete that as well. If we delete all of the references, if we just delete f, the future, the worker will just release that memory and let it go again. So let's try doing another kind of future-based function. We can do client.map. So this behaves a lot like any other kind of map. You give it a function and you give it an iterable, and it will map that function over that. We get a list of futures back, and we can see it is running the increment through on all of those. And we've got two workers, so it's doing two at a time, which is great. All of those were pending because we printed those immediately out. If we have a look at the futures now, we can see that they're all finished. We watch the progress bars go. And then when you have a list of futures, you can do client.gather to get all of those back, and that will block until all of the futures are completed if they haven't completed already. But this should just return for us immediately. You can see there's a comment here that just says doing client.gather is equivalent to doing future.result for each of the futures. But now we have these results on our cluster, right? We've done this calculation, we've called this function on this type of data, and it generated all of these keys. And Dask can use these keys for doing like deduplication and optimization. So we can run exactly the same code again. We can make a new array, and we can call client.map on our new array and tell it to increment. And when it creates those futures, it will calculate the keys, and the keys will be the same. And so it goes, oh, I've done that. I know what that is. I've got that. I can just give you the result. So if I run this bit of code again, we get our immediately finished futures. We didn't have to recalculate those because Dask is doing some intelligence around not double doing work. If we as a user tell it to do the same thing twice, it does it intelligently. So that's all the examples in this notebook. Now we've got 5 minutes to go for the end of the session. So let's dig a little bit back into distributed. So kind of where we started with Kubeflow and deploying Dask and Kubernetes and all that kind of stuff. Let's talk a little bit more about distributed clusters. So within distributed, as I said earlier, we have like a bunch of these cluster managers that will create a scheduler and workers for you from within Python. Now, I'm trying to remember exactly what's in this notebook. We can do this manually. Let me just pop open a terminal. Instead of using Python, I can just do Dask scheduler on the command line. I can do Dask scheduler. And this will start me a Dask scheduler on this node. And then if I open another terminal, I can do Dask worker, and I can give it this address, right? This is the scheduler's. Scheduler listens on 2 ports, right? It listens on this 8786, which is the TCP port. It uses like a bespoke protocol for doing this. And it also listens on 8787, which is like a web server for that dashboard. So if we tell the Dask worker, oh, you should connect to this scheduler on port 8786, the worker will connect to the scheduler. We should see it kind of register. There we go. And then if I make another, sorry, this is all getting a bit small. I'm going to move this over here and then make that bigger. If I do from dask.distributed import client, I can do client equals, I can give it that address. See, oh yeah, you should have seen in the scheduler log that you can see the client made a connection. And if we have a look at this client, it has 1 worker. So we can start things manually, right? It's just, these are just Python processes running on machines, but starting things manually isn't particularly pleasant or particularly fun. So we've built tons of tooling to do this for you. So the most basic cluster manager we have is one called local cluster. And the intelligent things that local cluster does is it has a look at how many CPU cores that you have in your machine. And I forgot to import it. It decides how many workers and things to create and how to allocate memory and all of that. It like inspects the system and it makes intelligent decisions. Now, it turns out that I've been slightly fibbing all the way through. In this binder environment, there's only 1 CPU core. And so when we did the auto detect in the local cluster, it's only made 1 worker. We've actually been oversubscribing the CPU all the way through this tutorial, but I kind of had to make a point about doing 2 things at once. Hopefully nobody noticed. So these cluster objects are really useful. You can pass them to the client, as you've seen in some examples, to auto connect. We don't have to care about what that address is because the cluster object knows what that is. We can do all sorts of configuration with it. You can inspect and have a look at the keyword arguments. Each cluster manager differs in what you can configure. If you're doing stuff on Kubernetes, you can set things like Docker images and those kind of things. If you're doing stuff on the cloud, you can set VM sizes, EC2 instance sizes, whatever it makes sense for that platform. It's got some quality of life features, like you can call get logs, and you can see, oh, these are the scheduler logs, these are the worker logs, and you can kind of get all of that back into your notebook session instead of having to be actually on those machines. We can get the URL of the dashboard and all sorts of stuff. And the last thing to kind of show in this example is that another very popular cluster manager is this SSH cluster. And all this does is SSHs onto other machines and starts those scheduler worker processes and gets them talking to each other. So you give it a list of host names or IP addresses. It'll run the scheduler on the first one. So commonly you just run that on localhost. And then the rest of the addresses are where you want the workers to be. And then you can use this cluster object in the same way, pass it to a client. So if you've just got a bunch of machines that you can SSH into without, if you've got keys set up so you can SSH without putting a password in, that's a very, very nice, straightforward way to pull a few machines together into a Dask cluster. So that's kind of it. That's the end of the session. We're at time as well. So thank you all so much for your attention. I'm just going to kind of finish up on this very final slide. Dask has been around since kind of 2016. It's continually being developed and made better and being adopted within more communities. You can find out way more about Dask on our website. We've got documentation, there's examples. This tutorial is like recorded and in places online. I really hope this has been helpful. And if you want to join in, head to the Dask GitHub. From there, you can find links to our Slack, our Discord, like all that kind of stuff. We're a very welcoming community. So if you have questions and you want to get involved, please do reach out to us. Now I'm going to hang around, like we are over time. If you want to go to other sessions, please feel free to go to other sessions. I'm going to hang around for like maybe another 10 minutes, answer any more questions that anybody has. I'm generally happy to chat in the comments and things. But yes, thank you very much. This has been a long session, 2 hours. So thank you for your time and see you all around. Okay, I see a question in the chat. So I'm going to answer this question. So maybe a silly question, but if the local cluster only shows one thread, how did the speed up happen on your delayed example occur? So that's because we had 2 workers. So there were 2 threads at that point, because I told it there were 2 threads. There was only 1 CPU core, but there were 2 processors. And so we're kind of relying on the Linux kernel to like handle the threading there. And all of those functions, we were just sleeping. So those processes were literally just sleeping. It was very easy for the Linux kernel to like swap it over. So it was a little bit of a cheat to like make use of some limited resources in the tutorial. Okay, another question. What would be the best doc to go to understand scheduler, cluster, and client? So everything is linked from Dask, docs.dask.org. But if I show you, if we just go to docs.dask.org, there's a link at the top to distributed. So you can see the distributed documentation. And there's like all sorts of stuff in here about how things kind of work, and stuff about the architecture, and you can click on, worker and see how the workers are communicating, and it really digs into like the protocols and the internals of things. Another question: is there any good book on Dask? I am aware of 2 that are being written right now. I don't think either of them have been published yet. Let me just go to Amazon quickly and have a look. Book. That has autocorrected me to desk book, which is not very helpful. Dask book. Okay, there's some data science at scale with Python and Dask. I am aware of this one. Does have good reviews, as does this Python data analysis. But I would keep an eye out. I think there's going to be a couple more books appearing in the coming months. I would expect it by the end of the year, at least. Okay, I'll give it another minute or so in case there are any more questions, but then I'm gonna hop off. Repo, yeah. So this link here, github.com/dask. If we go here, there's like a whole org with like tons of code in it. So you've got Dask. This is the like main APIs that we were using, the array, the data frame. It's got a lot of the like core stuff about delayed and futures and all that kind of stuff. We then have the distributed repo. So this has all the code for the scheduler, the worker, all the communication stuff. I work there quite a lot. And then all of the different things. So we have like Dask Kubernetes that I was talking about at the beginning for the Kubeflow and general Kubernetes usage. There's Dask Kubernetes. If you're into HPC, there's Dask Job Queue. All of the like deployment tools tend to be like a different sub-projects under this, mainly because they're driven by a different like community member. And then we've got a few other places you can go. There's the Dask tutorial, which has got a lot of this kind of tutorial material. Dask examples. There's also Dask stories, which is like use cases. And then we also have this community repo, which is we just mainly use the like issue tracker, and this is to kind of discuss community stuff. We talk about releases here, long-term planning, all that kind of thing. So yeah, if you're interested in the community, you can kind of watch this repo as well. Okay, next question. Am I at the in-person conference? No, I'm not at the in-person conference, I'm afraid. NVIDIA has only just opened up travel, and they hadn't said yes in time for me to like make arrangements for this conference. Originally, this was meant to be like a 30-minute talk, and when I spoke to the organizers about, oh no, I don't think I can travel, they were like, oh, we're doing virtual workshops. Would you mind pivoting to a workshop? Which is why this has kind of been a bit longer and a bit more kind of deep dive into Dask. But yeah, so I'm in England at the moment, but I will be at other stuff if anybody's going to SciPy or yeah, I'm going to ODSC Europe next week. It's my first event. So yeah, sorry that I'm not there in person. Next question. Do you know whether the Kubernetes operator uses node affinity? So you can do whatever you want with the nodes, basically, with the pods. So Python API tries to make things as simple as possible for folks that don't care about the details, right? They just want to set what the container image is, maybe how many CPU cores and memory the pods have, and then just kind of get into what they're doing. So if you're doing stuff from a Python side, it's a little, let me get down to the operator, a little challenging. On my task list for like the next couple of weeks is to allow you to provide a full YAML spec in Python. I think that would be a useful kind of compromise. But if you go the other route of creating clusters via the custom resources, here's like an example spec of creating a cluster. So under spec, you have worker and scheduler settings. Under worker, you have the number of worker replicas you want. And then you have a spec here. And this is a pod spec. And so you can set whatever you would normally set in a Kubernetes pod spec. So whether this is affinities or anything like that. And then we have the same in the scheduler as well. We have a spec underneath scheduler. This is also a pod spec for the scheduler container. And we're kind of setting all the networking stuff here. And then we also have a service under scheduler. And this is a full service spec. So whatever you can set in service, you can set here. The operator just passes this down to the lower resources. So you can configure whatever you like within these things. It's hard to draw a balance between how much do we expose as keyword arguments in the Python API and how much do we say you should go and use the YAML now. Like that's a line that I'm cautious about keeping. Is no is temporary and yes is forever. It's that kind of thing, right? I'm nervous about moving that line. So yeah, if you want to do affinities and things, go down the YAML road. Another question, if the operation is not vectorized, does it make a difference in performance applying a function on a Dask bag or a Dask column? When you say Dask column, I'm guessing you mean in like a data frame. So I would think of it like Dask bag is like using iterables and in Python, whereas Dask column, Dask series and things are using pandas. So under the hood, pandas has some like C++ extensions, C extensions, C Python, uses Numpy and things. So I would often expect that using a Dask column, a series is probably going to be faster just because the pandas community have probably put a lot of effort into optimizing that. Cool, great. All right, well, I'm going to leave it there. Thank you all for coming along again. I hope you enjoy the rest of the conference. Feel free to come and prod me on Twitter. I will put the slides up and tweet them out later. And good to see you all. See you around.